Hello everyone, this is Mr. Lee. In this video, I'm going to go with the free response question that we just did, but more specifically, I want to go over how we can use the equations to really justify our answers. So let's do a quick recap. If you remember in part A, we have a scenario where our box is struck and is sliding up, and then it's sliding back down. Now in this scenario here, I have the free body diagram that you're given, and it's worth a total of 2 points. So the biggest difference here is that while you're sliding up, the force of friction of course goes against the motion. So if the box is sliding up, the force of friction will be pointing down and vice versa. Now, in part B is asking you, between these three choices, will it take a longer time going up versus going down? Will the time going up be equal to the time going down? Or will the time going up be less than the time going down? And it asks you to utilize the information from part A to really help justify your answer. So what I want to do is, because this is a skill set that I think that we do need to practice, is how can we use the equations here and mix it in with our logic to really come to a solid answer? All right, so let's begin. Now, believe it or not, they actually left you a couple of clues within the prompt to help you solve for this. In part A, they asked you to create a free body diagram with no other components. However, if you remember from this unit, when we created free body diagrams, along with creating the free body diagrams, we also drew in the components because the components helped us solve the problem. So even though you don't need to create the components to actually solve the problem, for part B, having those components there really helps out a lot. So I'm going to do that. Now, if they specifically told you not to draw in the components, okay, and that's good. But what you can do is you can, on like a scrap piece of paper or somewhere else on the free response, you can draw in the components, okay, so that you're like creating little mental notes for yourself. So here we have FGY. Okay, so if this is up here, this is my coordinate. Okay, we have FGY, and let's do this one in orange. And here we have FGX. So this is FGX, okay, and it's pointing down and to the left because f of g is pulling the object down and to the left. All right, so here we have our component version of the free body diagram. Now here's where the magic comes in. Now what we can do is we can create a net force formula in the axis that it matters. So it doesn't matter in the y direction, it only matters in the x direction. So let's create one for the x direction. So anything on this side will be for the up. So we will say the net force along the x-axis of the object going up will equal to the mass times the acceleration. Okay, and the acceleration of course is in the x-axis. And it'll equal to negative f of f minus fg of x. Okay, and both of these are negative because it's pointing to the left as the object is going to the right, right? So it's going against that motion. And I'll draw in that chart later. Here we have negative f of x going down. So this is the object moving down. Max is equal to f of f minus fgx. Okay, once again, minus fgx because it's going to the left. F of f will be positive this time because it's going up. All right, so here we have our equations. And before we actually dive into how to solve this problem, there's a couple of things that we can do. One, we can look at this problem holistically. We were given 0 numbers. And that's actually very beneficial. Relying on numbers isn't the best way to approach a lot of these questions, because what you have to do is you have to be able to think critically and really tell ourselves, what is this telling us? So here we have forces add up, okay? So we have forces that add up. So we will have a greater force. So forces will increase. Here we have forces that subtract. Okay, or that deduct from each other. And so here we have a total net force, here we go, net force, that will decrease. Now this really helps because if we take a look at the equation for Newton's second law, F equals ma, okay, F equals ma, this is where we can see the proportionality. The one thing that never changes is the mass. Okay, so we don't really care about the masses, but we do care about how the force affects the acceleration. So if the forces increase, Okay, because the force variable and the acceleration variable are on opposite sides of the equal sign. They are directly proportional. If force increases, so does the acceleration. Same over here. If the force decreases, the acceleration also decreases because these are both directly proportional relationships. Now this really helps. Now what I want us to do, so we're not even taking a look at the paragraph yet, we're just setting ourselves up. We're priming our brain so that we can write it. There's a quick little reminder about the velocity acceleration table that we used to create. So velocity, acceleration, and let's see, speed up / slow down, right? So if you remember, we created this table. So we said that if the signs are the same, it'll speed up. Okay, it'll speed up. If the signs are opposite, it will slow down. It'll slow down. All right, now this is extremely useful because here we have a scenario where the object is slowing down, and here we have an object where the object is speeding up. Okay, and that's because this object has a positive velocity because it's going up the ramp, but the overall acceleration would be negative. Okay, and here we have an object that is going down the ramp, and the overall acceleration is also negative because it actually does slide down. So we have a speeding up scenario. All right, so that's just useful to know in your brain. All right, now for the actual paragraph itself. One thing that you have to be able to do is you have to identify the variables that you have to talk about. So what we just did is we talked about the relationship between three variables, and they were F, they were M, and they were A. Okay, and the other variables that the problem wants you to talk about is time and also the velocity. Okay, and how do we know that we're talking about velocity here? Well, if you take a look at the acceleration equation, acceleration is equal to the change in velocity over the change in time. You can find that on the equation sheet, right? So if we're talking about acceleration, and we're talking about motion in general, I'm pretty sure that the problem talks about the motion, then that means we're talking about velocity, okay? Any kind of motion is velocity. So what I want to do right now is I want to get rid of the variables that are constant, and that will, in this case, be mass. All right. So what you have to be able to do now is you have to be able to identify, all right, so what's going on here? All right, so when the object is going up the ramp, okay, when the object is going up the ramp, it has a greater acceleration, all right? And remember, acceleration means a change in velocity. So that means the object's velocity will change at a greater rate, meaning that the two forces are acting against the object. And one way that we can look at this is acceleration is velocity over time, right? It's not the cleanest explanation, but I'll show you how we can use that equation to really get to our answer. All right, now going down, we know that there was a smaller acceleration, okay? Therefore, the change in velocity, the object's velocity will change at a smaller rate, okay? It won't change quickly, okay? It'll gradually change. So this is a swift change, and this is a gradual change. And once again, we can use acceleration as velocity over time. And once again, it is not the cleanest way of approaching it, but it really does help you see how the proportionalities help. Right? So if we're taking a look at the relationship between acceleration and time, they are inversely proportional. So here we had a greater acceleration, so the time that it would have taken would have decreased. Okay, and here we have a smaller acceleration, so the time that it would have taken to travel that same distance, it would have increased. Now, the way that we can really go into this is if we actually expand this equation even more, because we know velocity is change in position over time. Okay, so acceleration is velocity divided by time. Velocity is change in position over time. Okay, so this is how we get position t squared, position t squared. All right, so I'm going to clean this up a little bit. Acceleration is position over t squared, position t squared. We know that the distance that the two objects traveled, right, it's the same distance, so this doesn't matter. This doesn't matter. And here we can really see how the proportionalities affect each other. If we have an increase in acceleration, we have a decrease in time. If we have a decrease in acceleration, we have an increase in time. So if you take a look at the answer key, you'll notice that you get a point for talking about how the acceleration affects it. So this is 1 point. And let's see what else. You get a point for acceleration. You get a point for talking about the net force. Let's see. What else can you get? You get a point for talking about the velocity, okay, correctly. And you get to also, let's see, 1, 2, 3. Oh, you get 2 points for talking about the force, excuse me. So 2, 3, 4, and you get 1 point for having a good paragraph. All right. Okay, so this is just how I approached this problem using equations. Now, towards the end, I did get a little fancy here by breaking down this acceleration equation. But if we take a look at the kinematics equations, we can actually find this equation here. If we take a look at xf is equal to xo plus v initial t plus 1/2 at squared. Right, so that's where this relationship really comes from. Okay, but this is just like the cleaner version, or a equals v divided by t squared. All right, so that's that for that video. A really tricky problem, but if you have any questions, feel free to send me a message. These are the types of problems that you'll more likely see on the AP exam, where you have to really stretch your mind and apply the equations with the concepts. Bye-bye.